Now, before we do the next problem, I want you to remember that if a line is horizontal, then its slope is basically equal to 0. Now, why am I mentioning this right now? I'm mentioning this right now because in example 4 it says, find the points on the graph of the function f of x at which the tangent line is horizontal. So this graph that I have over here is kind of a sketch of the graph of f of x, which is negative x cubed plus 6x squared. So that's kind of the general idea of what the graph looks like if you were to put it in your calculator. Now on this graph, there's a couple of spots where the graph becomes sort of horizontal for a split second. That's this point down here and this point over here. Those are the places where the graph becomes kind of horizontal. So if you were walking on this graph, you would kind of be standing and looking horizontally sideways. Those are the places where you're highest or lowest on the graph. Now, if you draw the tangent line at those locations, your tangent line would look something like this or something like this. It's going to be definitely horizontal. So these are the places that we're looking for in this problem. We want to know what is the coordinate of that guy and what's the coordinate of that guy. That's what we're searching for. And the question here is to find the points on the graph, the red graph basically, at which the tangent line is horizontal. So what we have to do is basically recall that horizontal tangent lines have slopes that are equal to 0. Now, in calculus, we don't use the language of slope anymore. Instead of using the word slope, we actually like to say derivative. So by asking us for the points on the graph at which the tangent line is horizontal, they are basically saying solve the problem where the derivative is equal to 0. That's what they want us to do, pretty much solve that problem. Now, again, I don't have a derivative, so I must find the derivative first before I can solve this problem. So let's go ahead and do that. So step number 1 is going to be to find the derivative. Find the f prime of x. And the way I'm going to do it is by first saying f of x itself is negative x cubed plus 6x squared. So then what would the derivative look like? So again, keep in mind that we're going to be using all the different power rule, constant multiple rules, and so on and so forth to do the problem. And keep in mind that even though I'm writing f prime of x, this is the same thing as df over dx. So it doesn't matter what the notation is, we still want the derivative. Now, first of all, we have a negative and we have a 6. Those are numbers technically, so we are going to be ignoring them. So we're going to be ignoring the negative sign and ignoring the 6. Also, between the two quantities, there's a plus sign, so that we ignore as well. All we have to do really is find the derivative of x cubed. The derivative of x cubed, bring the power down, then subtract 1. And also, find the derivative of x squared. The derivative of x squared, again, same deal, bring the 2 down and subtract 1 from the power. That's pretty much the answer. Now let me clean it up a little bit and get rid of all these colors. This is the same thing as negative 3x squared plus 12x. So that is the derivative, but it's not the answer to the problem that they wanted. Remember, step 1 was find the derivative. Step 2 is to solve the problem where the derivative is equal to 0. So solve the f prime of x equal to 0 equation. And so how do we do that? The f prime is negative 3x squared plus 12x, and we want to set it equal to 0, and we want to solve it. To solve it successfully, we have to factor it. So we can factor negative 3 right away because 3 and 12 are multiples of 3. There's also x squared and x. We can also factor out 1x. When we factor out the 3x with the negative sign, we're left with x negative 4. This is basically the GCF method that we reviewed when we started the semester. At this point in time, either x has to be 0 or x has to be 4. Those are the places where the tangent line is going to be horizontal. And it makes sense because the first one is right at the origin, so that makes sense to be 0. The second one is right there. It makes sense for it to be 4. So, you know, that's what we're basically finishing the problem with. So 0 is here and 4 is there. At those locations, if you stand on the graph, you're going to be standing at a place where the tangent line is horizontal. And that's pretty much the end of the question. Now in example 5, I'm going to try to do something similar, but the reason I'm doing example 5 is to show you that there are not always answers to these questions, right? So, you know, in this case, I got lucky and I found 0 and 4. There were 2 answers. There are times when the answers do not exist. There is no solution to the problem. Well, in that case, it just means that the graph does not have any spot where the tangent line is horizontal. So like I mentioned, example 5 is going to be similar to the example 4, except this time we want the slope of the tangent line to be 15. So instead of being horizontal, we want the slope to be 15. Well, the steps are going to be the same. So step number 1 is going to be to find the f prime of x. So remember that f of x is negative x cubed plus 6x squared. So the f prime of x is going to be negative 3x squared plus 12x. And step 2 is going to be the step where we solve the question f prime of x equal to 15. Why am I putting f prime of x equal to 15? I'm doing that because when I see the words tangent line and slope, that literally, that whole thing is f prime of x. Okay, so the slope of the tangent line, that is the derivative in calculus. So if you don't get anything out of this whole class with me, just know this. When I say slope of tangent line, that is the same as saying derivative. So in my case, I want the negative 3x squared plus the 12x to be equal to 15. So to solve this, this is a quadratic. We have to put everyone on the same side. So I'm going to move them all to the same side with the 3x squared and the 12. So that means the 15 has to move across. And when I move the 15 across, it becomes a negative 15. So the 12x is already there and the negative 15. And now it's all equal to 0 because we moved the 15 across. So to make life even simpler, I'm going to divide everyone by negative 3. That way the numbers become a little bit smaller, it's a little bit more manageable, and I don't have the minus sitting out in front. So that makes the problem a little bit less complicated. So when I do this, I end up with x squared. 12 divided by negative 3 is going to be negative 4x. And then negative 15 divided by negative 3 is going to be positive 5. At this point, I'm looking for two numbers that multiply to 5 that can add up to negative 4. Is there such numbers that multiply to 5 add up to negative 4? You may be tempted to say, yes, 1 and 5 with a negative 1 and a positive 5. But again, if you multiply them, you don't get positive 5. So maybe if you make them both negative, well, you multiply them, you get 5, but now you don't add up to negative 4 anymore. If you make the 1 positive and the negative 5 negative, again, it does not work out. So regardless of how you do it, this is not working out. And actually, it turns out that this problem does not have a way to be factored like this. So you have to use a quadratic formula. And keep in mind the quadratic formula says a is 1, b is negative 4, and c is 5. So the quadratic formula basically is a formula to give you the x. It says that x is negative b plus or minus square root of b squared minus 4ac, all divided by 2a. When I plug all the numbers in this case, I get negative negative 4 plus or minus square root of b squared, so that's negative 4 squared, minus 4 times the a times the c, all divided by 2 of the a's. And this is going to give us 4 plus or minus, let's see, 16 minus 20, all divided by 2. And that's the same as saying 4 plus or minus square root of negative 4, all divided by 2. And let's pause right here. This is already bad because of the square root of a negative 4. This means that this answer is not going to be real. There's no solution that is real for the square root of negative 4. By the way, square root of negative 4, you probably remember this from a previous class, it's 2i. It's not real, that's what we're saying. So what does that mean for us? It means that this problem has no solution. So in other terms, there are no points on the graph of the function where the slope is equal to 15. Now, why did I say no solution even though I'm writing an answer right there? In business calculus, we like real things. We don't want unreal answers. We don't want fake imaginary solutions. We want real solutions. So if your answer is not real, you could pretty much pretend like there was no answer. So even though all this work right here in the middle of the page was perfectly fine and acceptable, and you probably had to do that in a previous math class, in this class, because we are only interested in real answers, when you come across a non-real answer, it does not count. It's as if you didn't do anything. And so therefore, in this problem, there will not be a solution. So in other terms, if I were to graph the function, there is no spot on this whole graph where the tangent line has a slope of 15. Oh well.